Hi everyone, welcome to another video of PyML Studio channel. In the last video, we saw the details of the original transformer architecture and we discussed that training this model requires a warm-up stage. In this video, we will see why do we need a warm-up stage and what are the alternative solutions that do not need such warm-up stage. Let's start with a recap of the transformer architecture. For simplicity, we just consider the encoder part here, but please feel free to watch the previous video if you want to see the full detail. The diagram shown here is the encoder architecture, which receives the inputs as the sum of the token embeddings and the position embeddings. Then we have this repeating block, which is composed of two residual subnetworks. A residual block for multi-head attention, or MHA, followed by the residual block for the feed-forward network, or FFN. But to simplify this further, we can use the following diagram to represent both of these residual blocks, where the Ln is the layer normalization and the function f could either be the MHA or the FFN. As we discussed previously, we need a warm-up stage for training this transformer. That is, we have to start with a very small learning rate and gradually increase it to a max LR. Then after that, we can start decreasing the learning rate using any learning rate scheduler. But using the warm-up stage means that we have to carefully tune these hyperparameters such as the initial LR, the max LR, and the number of warm-up steps. So that was a quick recap of the original transformer model and its training using the warm-up stage. Now the question is, why do we need a warm-up stage? This paper titled On Layer Normalization in the Transformer Architecture discusses this issue in more details. Basically, if we choose a large learning rate in the beginning of training, training will be unstable. And if we use a small learning rate throughout the training, it will be very slow and inefficient. So the warm-up stage is a practical solution to overcome these limitations. The paper hypothesizes that this is due to the large gradients of the layers near the output layer at the beginning of training. Furthermore, it is observed that the norm of gradients will decay exponentially with depth. That is, the layers near the input have the smallest gradient norms, while the layers near the output have the largest gradient norms. So if we make the architecture too deep by adding more and more layers, this will lead to vanishing gradients problem. These issues arise because layer norm is placed outside of the residual block. As you can see in this simplified architecture, the layer norm is after the residual block and the output of function f are summed together. This particular placement is called PostLN Transformer. Placing layer norm outside the residual block hinders the easy flow of gradients during backpropagation to traverse throughout the network. So now let's see some alternatives to the PostLN architecture to resolve such issues. The first alternative architecture is called PreLN Transformer. The PreLN architecture places the layer norm inside the residual block. So as you can see, there is a free passage for the gradients to traverse back without any impediment. So it makes it easy for the gradients to flow through different layers. And this will resolve the exploding and vanishing gradient issues. So that means we don't need the warm-up stage to train the PreLN transformer. Let's compare the architectures of PostLN and PreLN side by side. The equations shown below these architectures show the order of operations for these two architectures, with XL as the input to this entire block and the output being XL plus 1. In the PostLN architecture, we first compute f of XL, then we add that to the XL in the residual block, and at the end we apply layer norm to the result. But in the PreLN architecture, we compute f of Ln of XL, and then we add the result with XL. Now let's look at the pros and cons of the PreLN architecture compared to the PostLN. The first advantage of PreLN is that we don't have the exploding or vanishing gradient problem, and the gradients are well behaved. As a result, we don't need the warm-up stage anymore, therefore there are also fewer hyperparameters to tune. So these are all good. But there is also a big disadvantage. That is the representation collapse issue. Representation collapse is a phenomenon in neural networks where the representations of the model become less informative or less diverse. And this will lead to poor performance compared to the PostLN architecture. So to summarize this comparison and put it into simpler terms, we can say that training a PostLN is harder than training a PreLN model because it requires the warm-up stage and also more hyperparameters to tune. But when a PostLN model is successfully trained with a set of hyperparameters that are carefully tuned, the performance of PostLN is better than the performance of a PreLN that is trained using the same hyperparameters. So far we have seen two architectures, the PostLN and the PreLN, and each one has some pros and cons. Another alternative which combines the benefits of both PostLN and PreLN is called residual, which is proposed in this paper titled Residual Transformer with Dual Residual Connections. The repeating block of the residual architecture is shown here with two parallel branches that are interconnected with a horizontal link. The branch in the left resembles the PostLN block, and in order to facilitate the free flow of gradients, the second branch connects consecutive layers together without any impediment. Finally, let's put all these three architectures together for comparison. From left to right, we see the PostLN, the PreLN, and the residual architectures. And we have two criteria for comparison. Exploding or vanishing gradient is the first criteria, and the representation collapse is the second criteria. As we saw in this video, the PostLN suffers from exploding or vanishing gradients, while the PreLN suffers from the representation collapse issue. However, the residual architecture claims to have resolved both issues and is basically considered best of the both worlds. And with that, we can wrap up this video. Note that knowing about the latest transformer architectures will be useful not only if you are working with such models, but also it can be useful in job interviews, as I have seen some questions asked during interviews. So I hope you find this video useful and learned something new. In the next video, we will see different alternatives to the multi-head attention, including multi-query attention. So stay tuned.